All right, so we are getting started talking about unit cells today. We're completely shifting gears. We're going to look at the solid state. That's what we're looking at for all this week. We're going to be studying the solid state, right? So in Gen Chem 1, we looked at liquids, we looked at solutions, we looked at gases, and now we're dealing with the solid state in Gen Chem 2. So we didn't deal with the solid at all in Chem 1 because we saved that for Chem 2. All right, so in the solid state, we have a crystal lattice. This is a word that we used way a long time ago. What does that mean? That means the particles are in a regular repeating arrangement. So if you look on the bookcase back there, right, all of those are crystal lattices. It's a regular repeating arrangement of atoms. Particles are close to each other, right? We have strong intermolecular forces at play in the solid state. And it's extremely ordered. Right? When we talk about it from an entropy standpoint, is this high entropy or would this be low entropy? Is this high disorder or is this low disorder? This is low disorder, right? So this is low entropy. It's rigid. It's not compressible, right? You can't compress a solid. Can't compress a liquid either, right? Highly ordered. This is all stuff that we talked about in Chem 1 as a frame of reference. So when we talk about the solid state, atoms are packed in the most efficient way possible, right? So this is a figure from a different textbook looking at marbles. See the different ways that these are packed in? Look at the space left in between versus this packing, right? This is this space left in between. Here's a figure from your textbook using oranges. There are two ways that we could pack those oranges, or you could pack them with these kind of diamond shapes in between, or you could pack them in the orientation that gives you the triangle, right? So in the solid state, the atoms are packed in the most efficient way possible, okay? And they're packed in there in layers. So again, if you look at the crystal structures on the back there, you see that they're occurring in layers. It's repeating and it's in layers. And so a unit cell is the smallest unit that gets repeated over and 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 over to make your full-on crystal, okay? Because a crystal is just the same unit repeated over and over and over and over and over. And those unit cells are defined by what we call lattice points, right? Because if a crystal lattice is a regular repeating arrangement, right, and we break that down to the smallest unit that gets repeated over and over, that's what we call the unit cell. Okay, so for instance, we have a unit cell that looks like this. Here would be my lattice points. That would be repeated over and over and over. If I had a unit cell that looked like this, here would be my lattice points. That would be repeated over and over. Or maybe I had a unit cell that had this shape, and it would be repeated over and over. Okay, so these endpoints that we are defining are called the lattice points. And when you repeat that unit cell a zillion times over, that's what gives you your full-on crystal. I think this figure is actually from your textbook. Right, so this is the difference between a unit cell versus an entire crystal. Does everyone see the difference between a unit cell versus the entire crystal? This is the smallest unit. You can think of this as a polymer, right, versus a monomer, right? A monomer gets repeated over and over and over in a polymer. So the smallest unit is the unit cell, and then the crystal is when you take that and you not only repeat it to the left and to the right, but you're also going to have layers coming forward and layers going behind. Okay, so if we were actually looking at a crystal, you'd have layers coming out of the screen towards you, you'd have layers going behind the screen, plus you'd have layers in both up and down and left and right. Okay, so we are only going to look at cubic unit cells. Okay, you can get a PhD figuring out crystals. You can become a crystallographer and you can go on your doctorate studying crystals using X-ray crystallography. You can do that for your entire career. So clearly we're not going to look at every cell type in a general chemistry class. We're only looking at cubic because these are the simplest and the math is the least nasty. Okay, so we're only looking at cubes. What are some properties of cubes? What are some properties of cubes? All the angles are what kind of angles? 90-degree angles. What about all the sides? They're all the same, right? So they're all 90-degree angles, and all the sides are equal, right? That makes them the easiest ones to talk about. because we're not dealing with any sort of different angles. We're not dealing with any sort of different sides. This is as simple as it gets. And there are three types of cubic cells that we're going to look at. We've got what's called the simple cubic. Now, some textbooks call it primitive cubic. It just depends on which textbook you're looking at. Simple cubic, which is the same thing as primitive cubic. Body-centered cubic, and face-centered cubic. We're going to look at all three of these, okay? And I'm going to do my best to represent three-dimensional objects on a planar screen. I mean, obviously there are limitations, but I think if you visualize, it'll help. Okay, so we'll look simple cubic, SC, body-centered cubic, BCC, and face-centered cubic, FCC. So this figure's in your textbook. I think this is the one that's in your textbook. Pretty sure your textbook calls it primitive cubic, which is the same thing as simple cubic, just FYI. So this is what's called the ball and stick representation, and this is the space-filling representation. So let's go through, just look at simple cubic first. And again, don't panic if you're reading online for some guidance or you're reading in your textbook. It's called primitive cubic. It's the same thing as simple cubic. All right, so if we're drawing a simple cubic, what are we drawing? A unit cell that has circles on each corner. Now, one of the things that just really blows your mind, especially at the beginning, is the idea that you have to take this unit cell and you have to visualize it in 3 dimensions, okay? You have to realize that all of these atoms on corners are being shared by other unit cells, okay? Because if I'm sitting on this corner, I'm not just by myself, right? When this thing gets repeated, left, right, up, down, forward, backwards, this corner atom is not just part of 1 unit cell. It's part of 8 unit cells. Let's talk about how that happens. So I made this drawing myself using a word processor, so bear with me. Let's imagine that we've got a cubic unit cell. Okay, now I made this one really, really big just so that it stands out. So if you're sitting on the corner here, you are part of this unit cell, right? But you're also part of the unit cell next door. Do we agree? And you're also in the unit cell below you. And you're also in the unit cell below you on the left. Does everybody see how this is part of 4? Right now we're just saying, yes, this is being shared by 4 unit cells. Where do we get their other 4? This is not just one layer, right? There are layers coming out. There are layers going back. So this unit cell is not going to be part of the cell behind it, right? This cell, if you imagine another layer back here, would this corner be part of the cells behind it? No. But if there's another layer in front of this, would this corner cell be part of those 4 unit cells? Yes, it would. Okay, so again, tried to do my best using my word processor here. So if you're on a corner, you're part of those 4 that I just showed you. And then when you put another layer on top of that, you're also part of those 4. Okay, so what does this mean? This is what you need to know. Okay, if you are in the simple cubic, what I would do in your notes, FYI, today, is I would make myself a running tally. All right, so cell type. So far we've only done simple cubic. Net number of atoms. Okay. Each atom is worth how much? I already told you, right? If it looks like this, and there are only atoms on the corners, right? If you're in this corner, you're part of this one, this one, this one, this one. That's 4. Plus the 4 in front of it, that's 8. So you are part of how many unit cells? 8. So each atom is worth 1/8, right? If every corner is worth 1/8 of an atom, which is what we just established. Now, how many corners are in simple cubic? How many corners? How many dots? 1, 2, 3, 4, 5, 6, 7, 8, right? So you've got 8 atoms, and 8 of them times 1/8. So how many net atoms do you have in the simple cubic unit cell? What's 1/8 times 8? 1, right? Now, I don't want you to think of it as just one big circle sitting there, because that's not how you get 1, right? You've got 1/8 plus 1/8 plus 1/8 plus 1/8 plus 1/8 plus 1/8 plus 1/8, right? There's a difference. I know you're probably going, you could say 1 pizza versus 8 slices. Well, they're different, right? Because if you've got a whole pizza that's not sliced up versus a pizza that's sliced into 8s, those are 2 different things, right? You've got the pizza that's sliced into 8s, not a whole pizza. So make yourself a running tally in your notes. I'm advising. I'm obviously not going to come check your notes. I would advise making yourself a tally. That's simple cubic. Because if you don't understand how many net atoms are in each of these, the math on Wednesday is just going to be a disaster. Okay, you have to know how many net atoms are in each cell type. And I know, like I said, I told you I was going to blow your mind a bit. I wasn't lying. Is everybody with me on simple cubic? Because from here it only gets worse. So do we understand how we came up with 8? If you're on corner, you're part of 8 unit cells. Yes? Because you're not part of, if you're on this corner, you're obviously not part of the ones behind you. You're only a part of the ones in front of you, to your left, to your right, and that's it. This guy would also not be part of a cell above it, right? Because it's in this cell. Okay. So each atom, each corner is worth 1/8. There are 8 corners, so you have net 1 atom. This figure's from your book. I think it's a nice representation, right? If you have this one in the middle, enlarged so that it stands out, right? How many unit cells is it a part of? It's a part of 1, 2, 3, 4, 5, 6, 7, 8. Okay? That's where it's being shared. So there's 1 total atom or 1 net atom in simple cubic. Now let's talk about body-centered cubic. What does body-centered cubic look like? Abbreviation is BCC. All right. Now, body-centered cubic is simple cubic plus this atom that is completely contained in the center. Is this atom right here in the middle being shared by any other unit cells? No, it's a prisoner, right? This one right here is stuck in the middle. It is not being shared by any other atoms. So if you think of this as just simple cubic, with a prisoner, how many net atoms would you have in simple cubic? Body-centered cubic. Let's go back to our chart. If we have body-centered cubic, BCC, what does it look like? It looks like simple cubic with a prisoner. Right? This one in the middle is trapped. So each one of these is being shared by 8 other unit cells, right? Is this one in the middle being shared by any other unit cells? No, it's not. So how many net? Well, you've got 8 corners that are worth what quantity each? What's a corner worth? Third, a half, 16? An eighth, right. So that gives you 1. And then this one in the middle, is it being shared by anybody? No. Plus 1 for your prisoner. So collectively, how many net atoms do you have in BCC? 2, right. 2 net atoms. Because you've got the 8 corners, and each corner is being shared by 8 other unit cells. Plus you've got 1 in the middle that's not being shared by any unit cells. Does everyone see how we came up with 2 net atoms for BCC? Does this make sense? Because really, if you understood simple cubic, then you should understand BCC pretty easily. Because the only difference between them is simple cubic doesn't have this center atom in jail, whereas BCC does. Right? And this jailbird isn't being shared by anybody else. Just try it there. So, figures from your book. Oh, I didn't have one from your book, just my rendition. Is everybody good on body-centered cubic? Does everybody understand why the net total is 2? All right. Now let's look at face-centered cubic. Face-centered cubic. I meant to bring some of these from home. We've got blocks galore, right? Blocks all over my house. Every brand, every shape, every kind, every texture, you name it, we've got them. Think about those really simple blocks that are cubes, and they've got the letters and the ABCs on them, right? You go A, B, C, the ABC blocks like 6-month-olds play with. That's a nice representation of the face-centered cubic. So face-centered cubic, see, you've got a picture. I like to bring the real thing, though. It's just better to see it and touch it. Face-centered cubic has 1 on every corner, plus it's got 1 on every face. Right? So if you're looking at these blocks that babies play with, right? This would be a face, this is a face, this is a face, this is a face, this is a face, right? So you've got 1 on every corner, plus you've got 1 on every face. Now, if you're looking at the face, how many unit cells share a face? It's not shared by 8 like a corner is. How many unit cells is a face part of? If you're on this face, you're part of this unit cell, and you're part of this unit cell, right? Would you be part of the unit cell in front of you? No, because you're not on a corner, you're on a face, right? Would you be part of the unit cell behind you? No, you're only part of the face next door to you, right? So if you're, snatched up next to somebody, right, you're sharing with that face only. So, how do we break this down? Let's talk about it. You've got 8 corners still. How many faces do you have on a cube? 6. 6 faces. Right? So you've got 1 net total, plus there are 6 faces, and each face is worth half. Right? Because this face is in this unit cell above it and this cell right here. That gives you a total of 4 in face-centered cubic. So if we want to finish out our chart, I think face-centered cubic is probably the most difficult to draw because you're trying to represent something three-dimensional in planar. All right, so face-centered cubic. Again, these are cubes, so all the edges are the same. So you've got 8 on the corners. All right, so you've got 8 corners. And each corner is worth 1/8. So 8 times 1/8 gives me 1. Plus you've got 1 on each face. There, right there, right there, right there, front, and the bottom, right? 1, 2, 3, 4, 5, 6. Plus 6 faces. And again, how much is a face worth? 1/2, right? So 1/2 of 6 is 3. So that gives us a net of 4. Okay, in your notes, make some sort of note to yourself to, I want to use the word learn, but I'm assuming you'll probably just memorize it. So I'm going to use the word learn. Right, because learn implies that you'll remember it forever, whereas memorize means you'll remember it until we take the test. So I'm going to use the word learn, but you can write the word memorize if that's what you prefer to do. You need to know this, okay? You need to know that there's 1 net atom in simple cubic. You need to know that there are 2 net atoms in body center cubic. You need to know that there are 4 net atoms in base center cubic. And you need to know how we got that, okay? You also need to be able to sketch each one of them to the best of your ability. I know FCC is especially difficult to draw. Right? 1/8 times 8, 1/8 times 8 plus the 1 in the middle, 1/8 times 8 plus half from the 6 sides. Is everyone with me on this concept of how we got here? Because if this doesn't make sense, calculations on Wednesday are going to be a mess. And they're probably going to be a mess anyway because there's a lot of details. So we want to make Wednesday as easy as possible by making Monday really, really solid. Is everyone with me? Have I lost anyone? We're all good. All right. So we are going to do some calculations today, but they're not going to be anywhere near as bad as what we're learning on Wednesday. So faces versus corners, right? Corners are worth 1/8, whereas faces are worth 1/2. And net number of atoms, 1, 2, and 4. That's just the summary right there. Any questions thus far? All right. 1 complete atom, 2 complete atoms, and 4 complete atoms. Trying to show you as many figures as possible. All right, so again, we're only talking about metals here. We're not talking about non-metals. These are all solid state metals that we're talking about, okay? And notice we're only looking at the 3 cubics. We're not dealing with anything hexagonal. This is HCP, hexagonal post-pack. Not dealing with that at all, right? We're just looking at cubic unit cells. We're keeping it as simple as we can. So let's look at some examples. I want you to look at this and figure out what's the unit cell type. See if you can figure it out just by looking at it. Has anyone figured it out? You only got 3 to choose from. It's body center cubic, right? How'd you figure it out?
Big one in the middle.
Big one in the middle is kind of a giveaway, right? You've got the 4 top, 4 bottom, and then 1 in the middle, right? That's body center cubic. Good. What about this one? Are you sure? It's not face centered. I'll tell you that right now. Look at the tops. Look at the tops. Is there something on the face? No, it's not simple cubic. Look in the middle. You've got a prisoner in the middle. So what's this one? That one's body centered cubic as well. All right, so I've got a handout that I'm going to give you. This is posted on the website. These formulas will be given to you on your next exam on the reference page, so I'm not expecting you to memorize them. And if you lose this or the dog eats it, whatever, and you lose access to the course website, you can just do an internet search of cubic cells formulas and get this formula sheet again. It's also in your textbook. Let's define our parameters here. We need to know this. Need to know, need to know, need to know. All right, so when we're talking about the calculations that are coming, that I have hinted at so lovingly, the calculations that we're going to learn on Wednesday are going to involve some of these as a starting point. Okay, this is just where we're going to start. So let's talk about where we get all of our information. All right, I think this marker works pretty well. All right, so A, I'm going to write this on your handout somewhere. A is edge length. Okay, so notice here's edge length. Right? There's edge length here. And here's edge length here. Okay? And R is radius. Right? So this is radius right here. Here's radius right there. And there's radius right there. So for any one of these, if I wanted the volume of the cell, for any cubic, how would I calculate the volume of this cell? How do you get volume of a cube? Cube? Length times width times height, right? So what would that be? Would that involve R or A? A, what would it be? A cubed, right. So just add that somewhere handy, because we're going to be calculating the volume of the cell on Wednesday. If you want the volume of any one of these three, whether it's face-centered, body-centered, or simple cubic, its volume can be determined by A cubed, right? Because A is just the length of this edge. And since they all have the same edge, right? The length of this side is the same as this, is the same as this, is the same as this. The volume of any cubic cell is just going to be edge length cubed. Okay? So just some important information to have in your notes on vocab and relationships. So let's go through these. This is all on your handout here. The relationship between edge length and radius. In simple cubic, edge length is equal to 2R, right? Do you agree with how that came to be? Because there's 1R, there's 2R, so to get all the way across, A equals 2R. Right? Do we agree with that? It's not too bad, is it? Now for face-centered cubic, we're looking at one of the faces. Okay, and we're going to think of it as a right triangle. So boom, boom, boom. Okay, and I'm just showing you the derivation here. I'm not going to make you derive it on a test. But just so you know where this is coming from, right, this hypotenuse would be 4R. Because think about it. There's 1R, there's 2R, there's 3R, there's 4R. Right? So we're using a right triangle, and I'm not going to make you go through the derivation, but if you go through the Pythagorean theorem and you solve for A, you get A equals square root of 8. Now square root of 8 is separate from the R. Okay, the R is outside of the square root. So it's square root of 8 times R. And that's how it is on your handout too. Make sure you have that square root and the R outside it. You're not taking the square root of R, you're only taking the square root of 8. So if you need to put parentheses around that square root of 8, do so, okay? Because if you're turning R into A or A into R, you're going to be turning R into A on Wednesday, okay? You're going to need A. We're not really all that interested in R. You want to have the parentheses around that square root of 8, okay? And then for body-centered cubic, again, we're going to be using the Pythagorean theorem. I won't make you go through the derivation. It's not nasty, but just so you know where it's coming from. You're going through the center atom, and you actually have to break it into 2 triangles and use one triangle as the hypotenuse of the other. I'm not going to make you derive where these things come from. But here's the relationship. That's what matters. A is equal to 4R divided by the square root of 3. And again, if you need to put parentheses around that square root of 3, do it, okay? Because the R is not under any sort of square root. It's just the 3. So this will be given to you on your next exam as part of the reference page, okay? It will not be something I'm requiring you to memorize, but I am going to expect you to be able to do the arithmetic. So let's do some practice. We're just plugging into the equations today, just easy stuff. All right, a new element, brachium, of course. Why wouldn't it be called brachium? Has been discovered. And brachium has a face-centered cubic unit cell with an edge of 4.070 nanometers. A crystallographer claims that the atomic radius is 1.85 nanometers. Is this crystallographer correct? So you try the arithmetic, see if you can do it. All right, let's go over this and see if we got the same answer. So we are dealing with face-centered cubic. So which one is that? The middle one, right. A is equal to square root of 8 times R. So is the crystallographer correct? What did you get? Did you get 1.85 nanometers when you plug in? I didn't. I got 1.43. Do we agree? Do I need to go through the math, or is everybody good on how to do this? All right. Answer this. Would the radius of brachium be different if it crystallized in body-centered cubic? And if so, what would it be? Try that one. Let's see what we got. Would the radius change if it were body-centered instead of face-centered? Would that make a difference? Yes, it does make a difference. I got 0.587. Did you? Did you? Can you make that switch? Point 7.04. Oh wait, radius is 1.85. All right, here's some more for you to try. I'm just going to pause the recording. Let me actually do it like this. Share screen. There we go. All right, here are 4 for you to try. Four for you to try. So I don't have to keep pausing it after every single one of them. So I'm going to pause it, let you try these 4, and then we'll go over them. All right, let's go through these. Converting between edge length and radius, radius and edge length. Again, I will give you the handout with these formulas. You just need to be able to use it. Okay. This is important prerequisite knowledge for what we're doing on Wednesday, which is why I want to spend the time today going over it. So let's talk about how we do the arithmetic, just to make sure there's no ambiguity on how we go through these kinds of conversions. I guess probably better start right there. All right, so we have FCC, face center cubic, and edge length. Is that A or R?
A.
A. All right, so A is 0.3615, and we want to know R, and we're told that this is FCC. So what's the relationship in FCC? A is equal to square root of 8 times R, right? That's our handout. So we're plugging it in. 0.3615 is equal to, what is the square root of 8? 2.8284R. So R would be this divided by this, right? 0.3615 divided by 2.8284. I got 0.12, let's see, we got 4 sig figs. So 1278. And what would my unit be? Nanometers, right? Because I'm given nanometers as my unit here. So my unit here needs to be nanometers as well. Do we agree on this one? Did you get anything different? If your last decimal place is because of rounding. Depends on how many decimal places you carried out square root of 8. Do we agree on how we do this? Square root of 8 we're treating like a constant. Okay, so it's not factoring into sig figs. We're basing off of these sig figs. And this 0 obviously is not significant. Questions on number 1? Feeling pretty good about how to do this? All right. Let's look at number 2. Would the radius of copper be different? What would it be if it were body-centered cubic? So, insert page break. We need our edge length, 0.3615. A is still 0.3615. And now it's BCC, and we want R. What's the relationship in BCC? A equals 4R. Right, A equals 4R over the square root of 3. So 0.3615 is equal to 4R over square root of 3. I round that to 1.7321. Just round it. All right, times 1.7321 times 1.7321. So times 0.3615. So 0.62614 is equal to 4R. So dividing by 4, I got R equals, we're keeping 4 sig figs still, 0.1565. And my units are still nanometers. That hasn't changed. Do we agree on number 2? Questions on how to do number 2? Feeling good on this? All right, let's look at number 3, which I'm pretty sure involves that same edge length. I think it asks us what it would be if it were simple cubic. Yep, if it were simple cubic. So if it were simple cubic, we have a different relationship, right? So what's the relationship in simple cubic? A equals 2R, right? So 0.3615 is equal to 2R. So dividing by 2, I got 0.3615 divided by 2. 4 sig figs still, 0.1808 nanometers. Do we agree on number 3? How to get that one? Questions on 1 through 3? Not bad, right? This is kind of the prerequisite knowledge we need going into Wednesday, so we want to make sure we're good at this. We've got one more to look at. So let's check out number 4. The atomic radius of vanadium is 134 picometers. It forms body-centered cubic unit cell. So radius, is that A or R? R. So R is 134 picometers. It's B, C, C. We want to know A. So what's the relationship in BCC? A is equal to 4R over the square root of 3. So this time we're given R, right? So 4 times 134 divided by the square root of 3. So 4 times 134 is 536. And square root of 3, 1.73205. Number of decimal places you carry out will factor into your sig figs, right? But it shouldn't make a huge difference. 536 divided by 1.73205. I got, within 3 sig figs, 309. And my unit is what? What's my unit? Picometers, right? Do we agree on this one? Any questions on how we convert between edge length and radius using our relationships here? Questions on any of the other conceptual stuff related to today? Number of unit cells, sketching, a number of net atoms, sketching a unit cell, how we share, any of that. Is everybody solid on those? All right. Well, then that is where we will stop for today. Wednesday we'll get into some calculations.